Hello and welcome to the second session of machine learning exercises. I hope you had no problems downloading the Anaconda distribution and running Jupyter Notebook on your PC. I also hope that you have had no problems with downloading the instructions and the dataset from DigiCampus. Now let's get started here. In this first exercise, we have a look at loss functions and the goodness of it. So, in this first part of the exercise, part A, we want to install the following packages: lmvar, ggplot, and dplyr. We will need them later. So I decided to do it the following way. You can give me feedback, by the way, if you don't like this style. But I decided to already use the notebook where I already run the code and show you the code and then run it in the session instead of typing it out myself, because this would be the other way I could do it. I could just type this all and then you would have to wait basically until I've typed it. So I decided to just leave the code here, show it to you, explain it to you, run it, and discuss the output and the code itself. I think this will be the most efficient way to do it. But if you have other ideas about it, let me know in the forums. And please try it out yourself first. So get to the instructions file without this code, try it out yourself, and either if you're done with it, then check whether your solutions are correct, or if you can continue, you don't know the solution, you don't know how to do it, then just check the necessary parts and go back to your file and try again, because I think this is the best way to do it. Okay, enough of that kind of talk. Let's go back to the exercises. So, right, we can install the packages with the install.packages command and then just the package name in here. And let's just run all that. Oops. Now. Okay, let's just run all that. Might take a few seconds. And I already installed it, so maybe your message will be a little different here. But it all worked out fine. So now let's import them to this notebook. And you import libraries with the library command and then the name of the library in here. So let's run this. And it shows some warnings, but let's just ignore them. And yeah, the libraries are installed and imported. We can go to the next part, which is the dataset. So in the instructions, I typed this name the wrong way. So it should just say real estate here. And you can find the dataset on DigiCampus as it says. And to now load this file, you first need to upload it to your repository. So here it's, let's see here. And it's a CSV file, as you can see. Let's go back to the session. Okay, and yeah, so I can read it with the read CSV command and then have the name here at the ending, which is a CSV file, so .csv. So read CSV, and we store the whole file in the variable df. So let's just do this. And it ran pretty quickly. So now we've got our data set. So let's go to the next part, which is the exploration. So as it says here, we should have a quick look at our data. The target or dependent variable, or also sometimes response, of the data set is the price. So it's got this name here. And yeah, every other variable will be the explanatory variables or features. So first, we should call the head function, the structure, and the summary to get an impression of our data set. So let's just do this. So here you see the head function, and the input is our variable that stores data. And if we run it, we can have a quick look at the first 6 entries here. So we see the variables and we see the entries. And now it seems like they are all numeric. But if we use the structure command here, str, and the input is our data frame, then we can have a closer look, and it says, yeah, they're all integers or numeric, which is fine for us. And they have 414 observations of 8 different variables. So seems all fine. Now let's have a closer look at our explanatory variable that we want to use in our later analysis. Because here in this bullet point, it says we are interested in the relationship or the influence of house age, which is stored in x2 house age, on the house price, which is stored in, yeah, you see this variable. And yeah, we should use a scatter plot then to see the relationship and say what we conclude from this observation. So let's first have a look at the summary of these variables. And you can see you have some statistics here which you should be familiar with, because they are pretty much the also the box plot information. So you have the minimum, the first quantile, the median, the mean, the third quantile, and the maximum in this of this variable, of our explanatory variable, and then the same for the response or target variable. So as you can imagine, we can draw some conclusions from this, but I think you've done this enough in the statistics lecture. So let's continue on and plot the relationship. And I've used ggplot command here. And our input of this ggplot command is the data, which is our data variable df, where we stored our data frame in it. And then which relationship do we want to plot? Well, it's the one of our x variable here and our y variable here. And then we specify the size of the points inside the scatter plot. So let's run this and have a look at the data. So what do we conclude from this plot? So it seems like for the first part, it's a downward sloping relationship, so negatively correlated. But then so excluding these data points, let's say, it would be clearly linear downward sloping. But if you include these, then it seems like it's upward sloping from a certain point. So it could be also a parabola relationship. We don't know, but those are two options that could be viable. So let's continue. And we want to examine the relationship now that we've plotted. We had some good guesses, and we want to have a closer look whether these are viable options. So our first model of these two models is a simple linear regression. As you can see, it's a first degree polynomial regression, so simple linear regression. And the second one is a second degree polynomial. So this would be a parabola. And yeah, let's just examine this relationship. X is our house H and Y is our house price. So these are vectors, as you can imagine. And let's go to the first model. So how do we do this? Now we want to store our model somewhere. And I use the variable name model1 for this. And then we store in it our linear model, which is which we can produce by calling the LM function, which stands for linear model. And then we need to specify which relationship we want to examine, and it's the relationship between the y variable here and this x variable. I could also set a dot here. This would then mean all other variables in this data set, and then which data set we want to specify in this part here where it says data equals, and then this is our predefined variable where we stored the data frame in. And then afterwards we want to have a look at this model. So we say print and then the model name. So let's run this. And it runs very quickly, as you see. And we see that that's the call, and our coefficients are the intercept of 42.43, and our beta 1 is minus 0.2515. So as you let's go back up here. So this would be starting somewhere here and then downward sloping. So let's have a look at our second model, which I called model 2. And now I specified it as the linear model with the linear model function, calling that. And the variable remains the same. And now I specify that it should be a polynomial of the variable x2.house.h, and the degree of the polynomial I can call here. So it's a second degree polynomial, and the data remains the same. And let's run this now. And as you can see, the intercept changes a little bit, and the other the betas are now different. So obviously there was no second beta here before, but also the first beta changed quite dramatically. So this would be now our parabola function. Now we want to maybe examine this relationship a little closer, or not the relationship, but our models. And we can do this using the summary command. So let's call summary, and the input of summary is our model name. And now you should be familiar with these kind of outputs. Yeah, let's have a look at our intercept first and our parameter beta 1. And we can see that they are both significant on the 1% level, which is indicated by the 3 stars. And yeah, we already had a look at the magnitude of the parameters. we can have a look at the R squared, which is pretty small with 0.04, which says that only roughly 4.4% of the variation within our y variable is explained by the model, which is not a very good model, to be honest. So let's have a look at the second model. Now we see our coefficients again, and we see that all intercept and both coefficients are also significant on the 1% level. But we can also see that the R squared really increased a lot and is now roughly 20%, which is much better than in the other model. So we can see that at least for the data that we are given, the polynomial relationship seems much more reasonable. Now let's come to the next point, which is the metrics. We want to compare the MSE, the RMSE, and the MAE of both models. You see the MSE, RMSE, and MAE here, and you've already discussed in the lectures what's special about them. You know that the MSE, for example, punishes outliers heavily. The RMSE is more interpretable than the MSE, and the MAE is maybe more straightforward than the other ones. So let's have a look at how we can do this. So as you know, we can just use our predictions here and the true values to calculate the errors. So first we need our predictions. So for the first model, I called the variable to store the vector of predictions in y hat 1. So to calculate the predictions, we can just call predict, and then the inputs are model 1, which is our first model, and the data frame df. And it will automatically store our predictions of the first model. Then we do the same thing for the second model and call this y hat 2. Now let's store our true values from the dataset inside the variable y, which would be then the yi's here. So this is pretty straightforward. We just call the column inside the data frame and store it in the variable y. Now let's define our n. This is also pretty straightforward, which is just the length of this column. And yeah, then we can go to the point where we just write these functions here in R code. So for example, for the first MSE, we have 1 over n. Maybe I can show you the functions again. So it's 1 over n here, and then times the sum over the squared deviations or squared errors here. And then the RMSE is very straightforward. It's just the square root, which is here the function sqrt of our MSE. And as you can see, it doesn't make any difference if you use this error symbol here or if you use the equal sign. So yeah, let's do the same thing for the second model, and then the MAEs, which is also pretty straightforward. It's 1 over n, and then the sum then let's take the absolutes of the difference or the errors. And you can imagine then that these are all vector calculations here. So we subtract one vector of the other and then take the absolutes of every value in the vector and then sum up the whole vector. And then obviously take that value times 1 over n. So let's run this code. And now let's have a look at the values. So let's compare the MSEs. And the MSE of the first model is higher than the one of the second model. Now, this is no surprise to us, as we also know that the R squared is higher for the second model. So if the model does a better job at explaining the variations in the y variable, then it should also have a better fit. And yeah, this assumption is shown to be true, as we can see here. So this now let's have a look at the RMSEs, and this should be the same. The first RMSE should be bigger than the second one, because as you know, it's just the square root of the MSE. And then the MAE shouldn't be any surprise, and we can see that also here this the first model performs better than the second one, according to the MAE statistics. Obviously, this is quite a lot of coding for getting these metrics, and we want to have an easier way to do this. And as before, we can just use a library for that and use the predefined functions. So let's use the library's metrics, which has a lot of metrics stored in it. So you can install it by running the command install.packages metrics, and then import the library to this Jupyter notebook by calling library and input as metrics. So, and then it's pretty straightforward. We just call the functions MSE and RMSE and MAE, and the inputs are just our predictions and our true values. So let's just do that. And we can see that the execution of the function is as shown below the cell. And we can prove by doing this that we didn't make a mistake in our upper coding here, and also the developers didn't make mistakes when they set up these functions. Could also be that both of us did a mistake, but that it seems rather unlikely. Okay, so let's come to the next point, which is comparing the metrics in general, which I will do by drawing a graph. Okay, now we want to draw our loss functions, and as you can see, I cheated a little bit and just copied in the loss functions from the lecture, because I think this will be much easier for you if I don't draw it by hand, because it's quite difficult to do with the mouse, and I think it will be a win-win situation if I just do it this way. And also this leads me to do a correction, which the professor also did in the lecture, and this is that red is not the MAE, but the MSE, and yellow is not the MSE, but the MAE. Beautiful. So, the professor also did this correction in the lecture, but if you haven't, I don't know, paid attention or so, then make sure you now know that this is the right form. So, what's the main difference? Well, if you have a look at the MAE, which might be the easiest one, then you see that it's just the absolute of the difference in prediction and the actual y value, which is the error, so the absolute of the error. And then it's obviously the mean of the, it's obviously the mean of that. So what does that look like? Just think about it if you would have only one observation. Let's just assume that we just have one observation. It's not very plausible in real life, but let's just do this for imagining. And now let's calculate the error. And let's say that we have an error of 1. So maybe our y would be 4, and then our estimate would be 5. Then we would have an error of 1. Now the absolute of 1 is also 1. So we would go here and say, okay, we have an error of 1. And then this is where our loss is, also at 1. And the same goes if the error was 2. We would go to 2, and the absolute of 2 is also 2. And that's how this straight line appears. If we go to the negative side, the absolute of -1, if the error here is -1, is also 1. And same goes for -2, that's also 2, and so on. So we have this nice V shape here. Now the MSE is a parabola form because it's the square of the error. So if you think that, for example, our error is 1, then we go to 1, and the square of 1 is 1. But if we go to 2, then it's 4, and so on. So this is how this parabola appears. Pretty straightforward. If you think of only one observation, if you have many observations, obviously, then you have the average, and then it's the plotting gets a little more complicated, but it's not that difficult. Just the scale changes a little bit then. So now let's go to the Huber loss, which is a combination of both, which basically says, okay, we want to have something like the parabola, which is like this parabola form, up until a point which we define, which is delta. Then we want to have a linear form. So up until the error, or the absolute error, reaches this threshold here, delta, it has the it acts as a squared function, so it's a little bit, it's not as steep as the MSE, and then up until a certain point, maybe here, it will become a linear function. The same goes for the other side, so it could be here somewhere, I don't know. So then this is delta, and delta is roughly -2.3 or something, or not -2.3, but 2.3. So this absolute of this error here is our delta value, and once this is met, this condition, then it will be a linear function afterwards. So let's go to the second exercise. We will discuss test train splitting and regularization now. So as you know from the lecture, there is a concept called overfitting. Overfitting happens when you fit your data, fit your model too closely to the data, and then it doesn't generalize well to out-of-sample data. There are different ways to avoid it, for example, regularization. But first of all, we want to know that we are overfitting or are not overfitting. And to be able to do that, we need to split our data set in two different groups. One is the test data set and the other one is the training data set. Or another word for test data set would be validation data set. So what we do is we train our model at the test data. Now, what am I talking? We want to train our data on the training data set and then test it on the validation data set. So we will compare the MSE from the in-sample estimation to the out-of-sample estimation. So we will need to import a different dataset for that purpose, which is the diamonds dataset. And the diamonds dataset is a part of the ggplot2 library, which comes in handy because then we can just import it by calling data, and yeah, the argument is diamonds. So let's save diamonds to df, and let's run this first, and then we can have a look at the structure. And the problem now is that some of the variables are not continuous but categorical. So this will be a problem, because how should we pass them to our model? Now, as you can see, there are only 5 levels, 7 levels, or 8 levels here. And the levels are basically unique values. So there are 5 different types of cut. There are 7 different types of color. And there are 8 different types of clarity. Okay, so these are all categorical values. And we need to transform them into numerical values. Yeah, we can also look at the summary of our data frame. And then we see here that for the categorical variables, you see the values and the amount of appearance in the data set. And yeah, for all categorical values and for the numerical values or continuous variables, you see the normal statistics from the summary as we've seen before. So we need to handle this problem. One way to do this is with one-hot encoding or dummy encoding. And yeah, you know this from economics. So what we do is we want to have a dummy for every single unique value or factor in a categorical variable. So if we go back, we have, for example, here cut, and that's like fair, good, very good, premium, and ideal. And then, so we want to have a variable that is equal to 1 if cut is fair, and equal to 0 in all other cases. So this would be the dummy for fair, and then we want to have this for every possible value. But the thing is that in the end, we need to delete one of those to avoid multicollinearity. So let's just do this and then come back to it, to the explanation later. So we will need a library to do this, otherwise it would be a large amount of coding, and we will use the FastDummy library for encoding. It's also possible with other libraries, but this is one very easy way to do it. So we will save inside our data frame variable. Oh, I'm being too fast. Let's first have a look at our data table again, and you see the values, and install the package FastDummies. I won't do this now because I've already done it. And now let's go and use FastDummies library. So yeah, inside our df variable, which currently has stored the data frame, we want now to save a new data frame, and this results from a transformation done with the dummies calls command. Now, I don't know if you're familiar with this notation, but so we want to specify that we want to use this dummy calls function from the library FastDummies, otherwise it won't work. And we do this by first writing the library name and then 2 times a column, and then we can just use our function as normal. So this term just specifies that the following function is from the library FastDummies. I see I need first to import the library, and now I can use it. So the arguments of this dummy calls function are our data frame, which is stored in df, and then we need to select the columns which we want to transform to dummies. And these are a list, and the list is written as a C, so a list of cut, clarity, and color. And we will remove the first dummy. So we have to call remove first dummy equals true. So we will avoid multicollinearity. Now let's do this. Let's run this cell and call head of the data frame to examine if everything worked out fine. Now you see that the dummies have been created. Seems all fine. Most values are 0 as expected. And now we still have the categorical features, which we want obviously to exclude from our data frame, and we do this by setting the respective columns to null. Now we can have a look again, and the columns will have disappeared. So no color or cut or clarity in here anymore. And let's just examine the names or the column names, and we see that they don't disappear anymore, and but instead we have the new color names here: cut good, cut very good, and so on, for our dummy variables. As I already said, we want to split our data into a training set and a validation set. The training set should be bigger than the validation set because we need a lot of data for our model to be able to extract the information from the data set. On the other hand, the validation set shouldn't be too small, so we have enough data to robustly test our data. Okay, because if it's too small, then you know, the likelihood would be too high that the random arrangement of the test set would distort the metric in any way. So, for example, it could be that they are just a cluster of very high values or very low values. So something that doesn't represent the distribution in the data very good. So you need a large amount of, or it should be large enough in the amount of data in the validation set, so you can actually draw a conclusion from that. Yeah, now let's fit a linear regression to a training set and then test it on the validation set. The target value variable is price, and all other variables or features from the diamonds dataset are our features. We will then compare the in-sample MSE of the training set with the out-of-sample validation set MSE. Now, let's first do this 80-20 split. There are some libraries that can do this, but I will show you a way I did it in a few simple steps. So first of all, we want to define the sample size. So how big should our sample be? Well, it should be 80%, so 0.8 of the length of our data set. And then this floor function just makes sure that it's an integer value, a round number. So next I will set a seed. So if so that when you replicate this, you will have the same distribution, random distribution, because we will random sample our data, and if you don't set seed, then the sampling can be different, the random sampling from my random sampling. Okay, so let's just set seed 42, and now let's define this variable, which should store all the indices that we want to, of the data that we want to have in our training data set. So we will do a random sample of our data. And now what we do is we say, okay, we want to have a sequence that is just all our all the indices that we have, okay? Because our data set is obviously has a lot of rows, and every row has an index, and we want to select the training data according to indices, and we want to have them randomly. So we want to have randomly sampled these indices. So this is just the sequence of all the indices that we have. And then we say, okay, but we want to have a sample of these. And the size of the sample should be the one that we define, so 80%. So we basically see draw a sample of a sequence of all the indices, or in the index values, basically, because this is just a sequence of values that we have in our data frame, so the length data frame. And the size of the sample should be the predefined one. And then what we do is we take these indices and we store inside this train variable the rows of the data set that have this index. And in the test set, we will store all the rows of the data frame that do not have these indices. Okay, so this is now how we split the data. There might be simpler ways to do this with a library, but I thought this would be a step-by-step solution how we get this train test splitting. Okay, so we random sample these indices, and then we attribute or the rows to the training or the test set. Yeah, let's run this, and let's have a look at the training data and also the test data. And it seems like everything's fine. So let's continue and build our model. Now, as we said, this will be a linear model. And our dependent variable, our target value variable will be price, and we will use all the features, that's why there's a dot here, as features. And the data will be our data frame df. So let's do this. I made a mistake. Obviously, we don't want to use all the data. We want to use just training data. So just call train. And now let's summarize the model. And we can see that many of the variables have coefficients that are actually highly significant. And now to calculate our MSEs, we need our predictions from this model. So let's continue. I mean, you can also have a deeper analysis of this linear regression output, but to be honest, I think you've done this enough in econometrics. So let's calculate the predictions. So this is the in-sample prediction. And for the in-sample prediction, we predict and use our model and use the training data. Okay, that's the model that's the data we've trained on. So this is in-sample. And our out-of-sample prediction we get by predicting our model and use our model for the test data. Now let's run this. And now we can calculate our RMSEs of the in-sample and out-of-sample data. And yeah, obviously we do this with the RMSE function and the respective predictions. And then also the, oops, this is not correct, this must be test. And also the true values, which is, oh no, this must be, sorry. Obviously this needs to be train. This is the true values of the price. So, and because of this being the in-sample, this must be the training, the price from the training data. And as this is the out-of-sample, this must be the price of the test data. So let's calculate the RMSEs and let's have a look at them. And we can see that the RMSE from the in-sample is actually lower than the RMSE from the out-of-sample. And this is not surprising, as the model fits on the in-sample data, on the training data, and therefore must be closer, or should be closer to the values in from the fitting process, from the in-sample data, from the training data, and therefore the error is smaller, but the error from the out-of-sample prediction is not not much larger. And this is a property of the linear regression, is that it has high variance and low bias. So it's not that accurate as a predictor. It doesn't predict that accurately, but if you change the training data, then it will be then the result will be not that different. And also this reflects if you then do the out of sample prediction. Okay. Then the next part will be cross-validation. So, as you've already discussed in the lectures, there are downsides to use this kind of splitting, to use for example, 80-20 split and then just check the out-of-sample performance. Because it could be due to sampling that the test data or validation data indicates that you have your model generalizes very well or it doesn't generalize very well. But this is not due to the model performance, but it's actually due to the sampling in the out of sample data in the validation set. Okay, so how do we check this? We can, for example, use cross-validation. And you have already discussed in the lecture how cross-validation works, how you use the same data set and split it into a training and test set, and then calculate the errors or the out of sample metric, and then you use the same data set and do another split, and then do this again, and you do this a number of times, and then you can have a look at the metrics, or you can, for example, use the average of these metrics and get the cross-validation metric, for example, a cross-validation MSE. And we want now to use this cross-validation technique, and we will use the package caret for that. As you can see, you can install the package with the install command, and yeah, just call the name caret, then we can call the library, and we could also set seed, but we already did this, so we don't have to set the seed again. Now we want to, as we defined, or as I asked for in the description here, we want to use a linear model. So we will define our model, we will store it in model 2, and as before, I want to specify that I use the caret package. That's why I write caret and 2 times the column. And now I call the train function. And in this function, I specify how my procedure should be during the training. What procedure should it be? So we want to use the price as the dependent variable, all other variables as features. Then our data frame is df. The method we use is linear, as a linear model. And now we want to specify what controls we use. So this would be then the function train control over the method CV, so cross-validation. Then I want to specify what kind of cross-validation I want. For example, 10-fold or 5-fold or 100-fold. So I want 5-fold. And I set verbose iter to false. I don't know if it's if I could actually delete this, because this could be the this could be automatically set to false, but let's just keep it here. So this basically says we don't want to have information after every training step, or after every step, after every cross-validation step. Yeah, and now let's just run it and then discuss it. So it takes might take a few seconds. And now we can print our model, since everything seems to have worked out fine. And yeah, let's have a look. Okay, so it was a 5-fold cross-validation, which also is written here. So resampling cross-validation 5-fold. Then this is the summary of the sample sizes. So this is 80% of the length of the data. And now the results from this are that there is a RMSE. So these are the cross-validation results. So the RMSE is 1131. The R squared is roughly 92%, and the MAE is 740. Okay, so these are the metrics of the cross-validation. So as you know, the cross-validation RMSE is the average of every cross-validation round, which in every round the RMSE will be calculated, and then the average is the CV RMSE, and that's this value. Now in exercise 2E, we have a look at the ridge regression. So first, what is regularization generally good for? Regularization is used to reduce the complexity of a model. A large number of features can lead to a reduction of the model performance due to multicollinearity or proneness of the model towards noise. The main reason for regularization is to prevent overfitting. The more parameters a model has, the easier it gets to incorporate idiosyncratic information of the training data to the model. This is especially problematic for models with a large number of parameters, for example, neural networks. Regularization can be achieved by modification of the loss function. Ridge regression and lasso regression use the L2, respectively the L1 penalty. The penalty term forces the model to decrease the parameters associated with the unnecessary features. In lasso regression, this can lead sum of the parameters to equal 0. The difference between ridge regression and simple linear regression is the L2 penalty term, and loss in the loss function, which changes the size of the model's parameters. So this also includes the explanation for the second question, what is the difference between ridge regression and the simple linear regression. Now the last part of the question is, of this exercise is use ridge regression on the diamond dataset, target and features specified as before. Also use test train splitting. What is the effect of a variation in the parameter lambda? So let's do this. First of all, we have to scale our data in the data frame. This is necessary so because if the variables are of different scale, which is normally the case, or often the case, then the betas will not be comparable. So we have to scale our data. Now, here I will split the data into train and test set, just as before. So test set is the validation set. Then in this cell, I have to divide my training set and my test set into y and x, because this is necessary for the later ridge regression. So here y train is a matrix of the column price in the train data set, and then x train is just the train data set, but I delete the column of price, so it will only contain the features. And then I convert the X-train matrix data to a matrix. And the same I will do for the test set. And then we can use the ridge regression. So we will use the GLMNet library, which is the one we also used in the lectures. So you can install it and then import it. And we will use a grid. And this is actually the same grid as we use in the lectures to find the right lambda. So the grid looks like this if you print it. And now to find the optimal lambda, we will use cross-validation. So this is the cross-validation of the ridge regression. It is a ridge regression because alpha is equal to 0. We use the X-train data and Y-train obviously as the targets, and then the grid lambda, the grid of lambdas here. And yeah, to find the optimal lambda, we can just after fitting call lambda min of the trained model or models. This is multiple cross-validation, and then yeah, call it with lambda min, and then we have the optimal lambda, which is here 0.01. And we can also have a look at the output of this cross-validation, and we see that the measurement was mean squared error, and the lowest of this mean squared error was lambda that has 0.01. Yeah, that's the lambda that produces the smallest mean squared error. So if we now if we compare now different values for lambda, we will use here the optimal one, and so just perform a ridge regression here. Then store the trained model in ridge regression or ridge reg. Then we save the predictions, and here we calculate the RMSE. So we do the same for two other values of lambda, 0.1 and 0.5. And now we can see that we sacrificed performance. And if you think back to the lecture, then this is what we would expect, because with more regularization we will increase the variance, but we will also introduce bias. And in this case now this is might be way too much regularization here, and so these are way too high error values or metrics. Okay, so let's go to the Lassus regression. And what is the difference between the Lassus regression and the simple linear regression? And the difference is that that we also, like in ridge regression, have here a penalty term in the loss function, and it's the L1 penalty. And yeah, we should also now run a Lassus regression on the diamonds dataset like before, and use just train test splitting. Now this is exactly the same procedure as before. We use the same grid, but now we set alpha to 1. So let's do this, and as you see, the optimal lambda hasn't changed. And then now let's do the same thing as before. We will now train a ridge regression with this lambda and calculate the predictions out of sample, and also calculate the RMSE. And then the same for a higher lambda value here, 0.1, and we can also do it with another one of 0.5. And we see that here it's even more dramatic. So if you have a look here, the increase of the penalty term did change the RMSE of the ridge regression less than it did with the lasso regression. So let's come to exercise number 3 about the bias variance trade-off. In 3a, we are asked, what is the bias variance trade-off? And explain it using the example of the test MSE loss from the lecture. So the bias variance trade-off describes the relationship between the generalizability of a model and the fitness of the model. And it also includes the complexity of the model, but we come to that later. So if we look at the decomposition of the test MSE, which you know from the lecture, we have basically 4 parts. So on the left side, this is the total error. And then we decompose it into these 3 parts, which is the variance here, the bias, and the irreducible error. So the variance indicates how much the prediction varies when we change the training data. So just imagine that you have a set of training data, and then you should make a prediction on a test data set, and you train the data set, the model on the data set, and then make the prediction, and then you use a completely different training data set and train the model again. Then if the variance is very high, it will lead to different predictions and therefore different results in the test data set. So that's the variance. So the variance is also high for very complex models and lower for basic models. And so the next term here is the squared bias, and the bias indicates the expected error when we predict the true values. So basically it's a measurement of how precise is our prediction, and you can see it easily when you have a look at the RMSE, for example, or the MSE. Then the last part, the irreducible error, is just all the variation that you have that can't be explained, or it's due to the variation in the y variable, which you can't explain with the features. And that can be due to multiple reasons. For example, if your data set doesn't include all the variables that could be used for the prediction, then obviously you cannot use the information that you don't have, and you will always have this error. So no matter how good or bad your model is, just because you don't have the information available in your dataset, you can't extract the information with your model, and therefore you will end up with a minimum error where you can't get below. And so the trade-off between bias and variance stems from the amount of complexity in the model. So if I have a very complex model, then it can lead to an improvement in bias. So just think back to, for example, the high polynomial regression from the lecture. That fitted very well the data set, but so it leads to a very low bias. You have a very good fit, but this comes on with the cost of a higher variance. So if you change the underlying data, then the results can be quite different. So in exercise 3b, we want to know, how does the bias variance trade-off relate to test train splitting from our examples before? So we use the test train splitting to be able to compare the out-of-sample predictive performance to the in-sample predictive performance. And these performance measures were the train MSE for the in-sample prediction and the test MSE for the out-of-sample prediction. And the bias variance trade-off links model complexity to this out-of-sample performance. If we increase the model complexity, the bias will decrease, which will result in extraordinarily good in-sample performance, so a very low train MSE. However, this is due to overfitting and will result in bad generalizability, so a high test MSE. Okay, because we fit very close to the training data, much closer than it would be. It would be if we would only model this true relation between, or this general relation between the features and the target, because when we model so close to the data, we will capture information that is not about this general relationship, but is due to this specific training data set. So it's idiosyncratic information that is not about this general relationship, but it's about this very data. Okay, and then if we use other data for prediction with this model, we will get bad results. So there's a trade-off between bias and variance when it comes to choosing model complexity. Underfitting will lead to a high bias, as the model has not learned enough information from the data, as it is too basic, and therefore lead to high total error. So this is the other side. If you have a very basic model, for example, a linear model where you, like simple linear regression, where you have just a line to describe the relationship, but the relationship is a little more complex, then you won't have any success for the prediction. You will do poorly and will be very imprecise. However, if you change the underlying data and therefore just train a new model on this new data, but it's the same complexity, so maybe also a simple linear regression, then you will get roughly the same data, you will get roughly the same model, the same relationship, because it's such a simple model. And when this model doesn't change, when you change the training data, then it's low in variance. But as a trade-off, if it's very low in variance, as it is so basic, this will also result in a bad modeling of the actual relationship if it's more complex, and therefore a high bias, so predictions won't be that accurate. So on the other hand, overfitting will lead to high variance, so the model generalizes poorly, which leads to bad out-of-sample performance, i.e. high test MSE, so high total error. Here's a typo. Okay, so this is the trade-off. If we have high complexity, then we have a high chance of overfitting to the data, and this will lead to high variance. And then we have we won't generalize well, and this will lead to bad out-of-sample performance, a high test MSE. So this is basically the relationship between the bias variance trade-off and our test train splitting. And now we come to part exercise 3C, where you want to illustrate this relationship with a graph. So we have here on the y-axis the prediction error, and on the x-axis the complexity of the model. And now if we have very low complexity, then as I said before, we have very high bias, as a very basic model can't model the relationship of a complex relationship very well, so it will have large errors. But if we change the training data, then the model itself won't change much, so it has low variance. But overall, this will still be a very high total error. So, and that's also called underfitting, okay, because we could do better with our model if we just increase complexity a little more. So let's do that. Let's increase complexity to the point where it's overfitting. Then, as I said, we have low bias, which you would be able to see, for example, in the train MSE. This would be very good. But then when you have a look at the out of sample MSE, this will be very bad. And this also results in high variance. So if you change the underlying data when it comes to training and you train again, then it could result in a total different model, and so also different predictions. And this overall leads to a high total error. So there is this trade-off, and if you can see, you've probably guessed it, there's this sweet spot where you have just enough complexity so you reduce bias a lot, but you haven't increased complexity so much that it would lead to high variance. And this is the point where we want to end up. So with a model that's not too complex but not too simple, and it's just right. So this also would be a model that has a very good train MSE, but a very good test MSE as well. So you could improve on the train MSE when you're here still, but this would come at a cost for the test MSE, for example.